Very good. On Cluster Algebra, Riemann integrals.
One of those? Yes, I think yours was pulled out. Oh, which it's Mike's, no? Into the path. Yes.
Left.
Dico pointers, ναι. Σε λεπτό να κλείσω το Wi-Fi, να συγχωρευτώ ότι έχει συνδεθεί, ωραία. Και μετά χρειάζεται να μπω στο Zoom βεβαίως, έτσι δεν είναι. Οπότε να μπούμε στο Zoom. Ωραία. Χωρίς όριο. Ωραία. Τώρα κάνω share screen, σωστά.
Can everyone hear me all right?
Yeah.
Okay. All right, so let's start. Thank you very much for the invitation. It's a pleasure to be here. And we should give a special thanks to the organizer, not only because they made it into an in-person conference after so long, but because it feels completely natural, even though it happens for the first time for all of us. I guess for many months, it feels completely safe with all the distances and the rules, the reasonable rules we observe. So yes, well done. All right. And here, yes, it's a pleasure for me to present some recent work that resulted in a PRL article together with Dima Cice and Johannes Hen. And this was also very recently awarded the Best Paper Award by our local cluster of excellence in Hamburg. So, the main player of my talk will be scattering amplitudes, which are the arena where perturbative quantum field theory confronts experiment. Let me put this. Okay. As we heard from Matthias, this is not the only ingredient, of course, but it is a very, very important ingredient. And we will also hear in later talks about the precision frontier. We shared, in fact, this morning already in very interesting talks that we are entering the precision era with respect to LDLHC. And this improving the higher orders, improving the perturbative expansion, going to higher orders, is important both for determining standard model parameters, but also, perhaps more importantly, for being able to tell apart physics from a huge, normally huge standard model background. And I think this is especially relevant. We will hear another talk about the high luminosity LHC, I guess, 2 days from now. But currently, the only approved major experimental upgrade is the high luminosity LHC. So no increase in energy, just increase the number of events. So using precision to be able to spot rare events and so on will be one of the main tasks of the upcoming years. So these are the things that excite me in this precision frontier and why I think it's important. Of course, it's very hard and you run out of steam very fast. And before you turn into a version, this talk will not be about n equals 4 super-Yang-Mills theory, will not be about the simplest interacting gauge theory, but it will be about how to successfully import some of the lessons we learned there to realistic physics. Because in the past, there have been many, many success stories where in this ideal theoretical background, we were able to first do a proof of concept of new methods that were then refined and further developed in order to attack the standard model and beyond. And some examples, of course, are generalized unitarity that solved the one problem forever for every quantum field theory, and it was first done in the context of n equals 4. More recently, the method of symbols that I will hopefully be able to talk about and define. And very related to this is also the method of canonical differential equations, how to recast your master integrals for any process in a very nice form that essentially is equivalent to actually evaluating the integrals. And all these were first understood and formulated in the world of n equals 4. And just to showcase their importance, one of the state-of-the-art computations involving 5-point two-loop integrals with one mass, which are, for example, relevant for W boson production plus two jets. Yes, these would be the jets, the collimated arrays of particles of yes, from the partons that we also heard about in the previous talk. And I should also point out that Greece is making major contributions in yes, understanding these classes of integrals. The group in Democritus have provided fully analytic and very well controlled expressions for these kinds of integrals. But the point here is that indeed there is something to learn from importing knowledge from doing knowledge transfer from n equals 4. And with this general motivation, let me talk about cluster algebras. This will be one of the main themes of my talk. And these are beautiful mathematical objects that have been tremendously successful in describing singularities of n particle amplitudes in n equals 4. And this is one of the reasons why I have been very much focused on understanding and using these structures that have, as I will explain, really led to results for the 6 and 7 particle amplitude in n equals 4 to unprecedented loop order. And so from the lessons we have learned in the past, it was very, very natural to pose this question. Could cluster algebras, this beautiful and useful structure in the realm of n equals 4, could it have wider applicability? And in order to search for it, we looked at Feynman integrals because they are theory agnostic, they appear in many different theories. And we looked in dimensional regularization because you always have divergences that only at the very end you can cancel them, and this is the most natural, arguably, way to do it. And to our great surprise, we found that this kind of cluster algebra structures encode singularities also in a wealth of physically relevant examples, including QCD corrections to amplitudes that enter the computation of heat plus jet production in hadron colliders. So I am personally very, very excited and look forward to understanding it in the future. But this is, if you wish, the extended abstract of my talk. And now let's try to focus, yes, and explore in more detail all these topics. So let me define cluster algebras for you, since it's one of the main concepts. And very roughly, they have some basic ingredients. One of them is some set of variables that are also called cluster A coordinates. This is what they are built of. And these variables, they are grouped into overlapping sets. Overlapping means that the same variable can appear in many different sets. All these have the same size D, and these are called the clusters, hence the name cluster algebra. And what is remarkable about cluster algebras is that you don't know what you will get from the very beginning. It's like chess. You have a certain set of rules that are called mutations, and you play this game, and in the end, you generate your cluster algebra. But let me give you an example that will be the main example of my talk, the C2 cluster algebra. This 2 is the rank, so it means we have two variables. And the cluster coordinates are labeled by a single integer, m. And the initial cluster has size 2, as we said, consists of the first two variables. The remaining classes are A2, A3, A3, A4, and so on. And for this case, this is what it turns out to be the mutation rule. So you get, for example, A3 to be equal to 1 plus A2 over A2 squared over A1. And you keep going. So this is what I just told you. You keep playing this game. You use this formula again with this when m is odd. You can replace A3 from the formula you just obtained. Evidently, whatever you will get will be rational functions of your initial cluster variables. And you keep doing it and doing it. And very interestingly, after you do it 6 times, you end up to where you started. So you don't get anything new. And you can also visualize this, the topology of this cluster algebra, with so-called an exchange graph, where the nodes are the clusters, A1, A2, A2, A3, A3, A4, and so on. A line is a mutation that relates them, and you have a circle topology because you're back to where you started. So this is the particular example of cluster algebra. You might ask, okay, but this is specific. How about more general cluster algebras? And the need is really this mutation, this kind of mutation operation, how you define this more generally. And I will skip the long formulas and just give you one big class which you can geometrize, you can visualize what this mutation is. When cluster algebras are finite, you can classify them by Dinking diagrams. So for the AN case, or SUN algebras, you can think of a cluster as a particular triangulation of an n plus 3 gon. So the A3 is a hexagon. You here have a hexagon, and you have a non-crossing triangulation. The chords are they're splitting it into triangles. They do not cross, and these chords are themselves the cluster coordinates. And you can figure out that you have different choices of this type, and the mutation in this case is just flipping a diagonal in any rectangle subdiagram. So you perfectly geometrically define. In this example, just pick the middle rectangle and flip this diagonal. So replace it with this diagonal. This is what you obtain. And you keep going, and you keep going, and you keep going, and you keep going. And in the end, you generate something which is now 3-dimensional, because this is a rank 3 cluster algebra. And you can convince yourself that there are 14 different kinds of triangulations, and they are related in this way. And I should say this is an A2 subalgebra of this cluster algebra, because you keep one of the edges fixed. You see all the edges here are fixed. So this is effectively like a pentagon, and you obtain this pentagonal subalgebra. But now that I have defined them, let's see how they come about for scattering amplitudes and for quantum field theory. And for this, I need to first of all tell you about this function space of multiple polylogarithms. This has found numerous applications in general quantum field theories. And for n equals 4, there is a great deal of evidence that L-loop amplitudes are functions of this type with weight k equals twice the loop order. There are general arguments and explicit computations to which I have also contributed. And probably you may have seen this before, but MPLs are a generalization of logarithms or classical polylogarithms, and they're defined recursively by this differential. Such a function of weight k has a differential of this sort, where the important part here is that you strictly reduce the weight by 1. So a logarithm, of course, is part of this class where this f is weight 0, namely rational functions, the dilogarithm as well. An important and convenient tool for describing them is the so-called symbol, which essentially encapsulates this definition multiple times. This is a recursive definition of the symbol where you can compare. I have essentially rewritten the same thing just by replacing the d log with just a tensor product, and then I apply the symbol map again. So I take the differential of fk minus 1, and then I keep adding more tensor products and let's say different phi's that are next to each other means that the functions are related by iterated derivatives. I differentiate again, and so on. So the collection of all these phi's that are rational or algebraic functions of your external kinematics is called the symbol alphabet. So now that we have defined our functions, let's see what cluster algebras do for us. Cluster algebras provide the right variables to describe these functions. And now that we have defined them, let's say instead of right variables, I should say, tell us for us what the symbol alphabet of these functions are in this very general class. And I was strongly motivated by the Brown group. It turns out that precisely these letters, the symbol alphabet, amplitudes in n equals 4 are given by GR4, n cluster algebras. You don't need to know exactly what these are, but you already know, in fact, one of these examples. This is the A3 example I showed you. So you're already familiar with one example. Another one is the E6, which is also finite. But physically, it's easy to see from the previous definition, from this d-log, that when the phi's go to 0 or infinity, these tell you potential singularities of your amplitude. So this is what their physical significance is. And just to showcase their importance, I will not mention the long list of papers I had in the second paper, but there is a very nice, I believe, review of this field based on a talk I had given here 2 years ago. You can actually use this information. It's a crucial ingredient for computing the actual amplitudes via the amplitude bootstrap method. And the gist of the method is that you first construct all possible amplitudes, let's say the space of candidate amplitudes. This is what this blob, like a Venn diagram, means. And you will pin down, you identify the single part of the set, which is the amplitude itself. And through the work that I have led in the past years, the 6 particle amplitude is known to 7 loops, and the 7 particle amplitude to 4 loops. So much higher than the 2 or 3 loop progress that has been achieved for realistic gauge theories. So this is perhaps why one could harness this power. There's one more technical thing that I would like to tell you before I end this introduction, and is that so far I have only talked about cluster variables, not about the cluster themselves. Do they play a role in amplitude, the actual clusters, how these variables are grouped into each other? And it turns out that they do. They can only appear next to each other in the symbols, 2 of such cluster variables, if there exists a cluster when containing both. And in this example of A3, I told you that cluster variable clusters themselves consist of non-crossing diagonals. Therefore, you will never find a cluster where diagonals cross. So the variables that correspond to these crossing diagonals can never appear next to each other in the symbol. We have a physical understanding through the work of my collaborators and myself about this particular absence of forbidden letters. Because it's related to the standing relations, and it turns out that it implies the rest. But very importantly, it massively reduces the size of candidate alpha amplitudes, and that's why it gives you so much power. If this was very technical, let me summarize the introduction or the review of the n equals 4 world by an analogy that I would dare to draw between the symbol of the amplitude in n equals 4 and the DNA. The DNA, of course, is a double helix, as we all know, but for the sake of the argument, we can unwind it. We can follow a zigzag path around it and then turn it linear. And of course, the symbol is also a tensor product of different spaces, of different letters. So evidently, cluster variables play for the symbol the role that bases play for the DNA. Perhaps, yes, equally importantly, since this comes from a helix, we know that adenine only goes with thymine. You cannot combine it with the other bases. And similarly, adjacency has to do with the pairs of letters. So the question we try to answer is, could cluster algebras more colloquially provide some sort of genetic material, not just for n equals 4, but for generic quantum field theories? And this is what I will focus on in the main part of my talk. Where do we look? What we did was to look at scalar Feynman integrals with massless propagators in dim range. And as I said, integrals are theory agnostic. They appear in different theories. That's why there is no loss of generality when considering scalar integrals. You can reduce tensor integrals. The dimension is 4 minus epsilon because we take epsilon to the 0 only at the very end. And the only real assumption was this massless propagators. That is a very natural thing to do if you come from the n equals 4 world, and it's a simple starting point. I just flash one loop example just for my notations. A double box means a massive leg in this instance. The dimension is here. And just to remind you that for any given set of integrals, let's say those that contribute to a process, there are relations, integration by parts identities. So basis in this vector space is the so-called master integrals. And the main example that for different reasons we focused on is this 4-point functions with one of shell length. 4 particles because we would like to have scattering, not just decays, and 1 massive leg because we'll see. But in any case, from the kinematics, it's easy to realize that you in fact have just 2 independent variables. These are massless legs, so only the cross products are meaningful. Due to momentum conservation, they satisfy this constraint. So you have 2 independent variables. And long time ago, German and Remedi analyzed what the alphabet is. And as we see in this example, there are 6 letters that are linear functions of the kinematics. They're called 2D HPLs. And also, yes, these are the master integral studying. More recently, there is also a 3-loop family that was studied, both planar and non-planar, you see. And so, having focused on this example, comes the question: how do you identify the cluster algebra? How do you associate one with a particular process? And there are some necessary conditions, like the number of variables. We saw that it's 2 for 2D HPLs. And for example, there are also 2 in the A2 example. However, if you go and you count the number of letters, you see a mismatch. And this was for a long time one of the stumbling blocks of why people from, let's say, the n equals 4 world hadn't thought of applying this technology to the real world. In the n equals 4 world, we only have simply laced groups, A, D, or E. And it was this discussion that we were having in Edinburgh right before the lockdown in a very interesting workshop with Johannes Hen, when he pointed out to me this mismatch. We were lucky to be in the same bed and breakfast, and I thought about it, and I told him, you know what, there's another cluster algebra, C2. We saw it, it's the hexagon we saw in the second or third slide, that has, yes, 6 clusters and 6 variables, and the numbers match. And then we went on and looked at weight 2 combinations, weight 2 symbols, and the numbers matched as well. Weight 3, and we can keep going. So this gave us great certainty that whatever was known in the Fino literature must have been related to the types of cluster variables I also presented you early on in the slides. And the question was how to relate the two. I will not go into the detail, but it's a very simple transformation, and there's a systematic way to get it. Once you are pretty sure that the alphabets are related, are equivalent. And so the conclusion is that these very known class of functions are in fact polylogarithms related to the C2 cluster algebra. Okay, but what is the physical significance of this class of functions? So the master integrals that are expressed in terms of 2D HPLs, they appear in many physical contexts, important physical contexts. They were initially used for deep inelastic scattering, but if, leptonic scattering is not your thing, they also appear, let's say, in hadronic Z-boson production. And perhaps more importantly, because the Higgs is made one of the stars of the last 10 years or so, they also appear in Higgs plus jet production in hadron colliders. That is in the heavy top mass limit where one integrates out this fermion loop. And this is very, very reasonable, and it appears as a desired experimental approximation, say, in the Lezus wishlist. So I think, yes, for us it was very exciting that this mathematical object underlies Higgs amplitudes. Of course, having found it, there is a natural question, what does it buy you? For sure, it points to you this kind of adjacency properties, what kind of letters can appear next to each other in the symbol. For this, it's easier to use the canonical differential equations approach. Now, as I'm running out of time, I have to speed up a little bit. But the essence of having a basis is that you differentiate it, you're back into the basis. And in the clever change of basis that Johannes recommended, you have an explicit epsilon when you differentiate. And this makes your life easier. You have some constant matrices, and then whatever is, the letters of your multiple polylogarithms that your master integrals evaluate to. And then any kind of adjacency property can be translated into a statement about these matrices to all orders in epsilon. So that's the benefit that you gain. And so these kinds of relations are very important, say, when you try to analytically continue your function. You start from the Euclidean region, you want to go to some physical region. This means that you will not have certain iterated discontinuities, and it will make your life easier. So what did we see? What did we find for this particular class of functions? The cluster algebra revealed for us that there are indeed this type of adjacency relations where A1 can never appear next to A3, not next to A5, and so on. And you see indeed that A1 never appears together with A3 in a cluster. So this is consistent with the notion of cluster adjacency, and this was something that was not observed. These integrals and these functions were known for a long time. No one had observed this, so we did learn something new about them. And just to highlight their importance, assume that you were looking at the space of functions containing these integrals to 4 loops, or weight 8, without this property and with this property. You see that this space is less than half when you are also demand that this kind of adjacency condition appears. And so you have very fewer choices to look for, let's say, your physical quantity. And this has already been applied in parallel work by Dixon and collaborators in bootstrapping an analog of the Higgs amplitude in n=4 world. So with this, I will go to my conclusions because I'm out of time. There are several more examples that you are welcome to ask if you are interested, including how to go from the 8 particle amplitude in n=4 to 5 gluon scattering in QCD. So I invite you to ask. But I hope I convinced you that the beautiful mathematics of cluster algebras seems to underlie a wealth of physically relevant Feynman integrals and processes. There are interesting things to do in the future to see if this is more universal or we just got lucky. But if you wish as a vision, and something I would very much like to understand, is whether cluster algebras could provide a kind of organizing principle, or if you wish, genetic materials that would simplify future collider physics calculations. Thank you very much for your attention.
Thank you very much for this fascinating presentation. Yes, questions? Yes. Go ahead. You mentioned linking diagrams which are used for the algebras. Can you better explain the connection between cluster algebra and linking diagrams?
I could be talking for another hour about this, but one way the connection appears is because you can represent, so I gave you the geometric representation of some of the simplest like class of cluster algebras. More generally, you can encode the information of every cluster of its variables and how you can reach other clusters by mutations by quivers, oriented graphs. And it is a theorem that whenever your quiver looks like a linking diagram, then this is related to the Lie algebra of the associated Lie algebra. So this is one way that one can establish a connection with Lie algebras. But I should say that cluster algebras, as you saw from the example, they are commutative algebras. So you really multiply these factors together. There is nothing non-commutative there. The relation with Lie algebras has to do with the quivers encoding them, and ultimately to, as you saw, this kind of topology and geometry of the cluster algebra.
For 1 hour. Okay.
Thank you.
Yeah, very exciting talk, and I wanted to come back to this last point that you're making here in the box. So, trying to understand what you have in mind. Are the cluster algebras more general or the Feynman graphs? I mean, does every Feynman set of Feynman integrals have a cluster algebra, or vice versa?
We don't know because we are just barely scratching the surface. We just discovered the tip of the iceberg. I should say it's almost entirely clear that cluster algebras are not the end of the story. And this is what I have here in this slide. At least in the n = 4 world, the relevant cluster algebras, when you go to 8 points and higher, I talked about 6 and 7 points, become infinite. So this gives you it's a big puzzle, because if you have infinite choices, then we lose all predictability. And in this work with my student 2 years ago, that was simultaneously with work also from US group centered at Brimstone and another group in Southampton, we resolved this issue. We found an appropriate generalization that is finite. Also, at the same time, I haven't included it here, we generalized the functions because if you noticed from the simple example I mentioned, all the letters in cluster algebra are always rational functions of your variables. Of course, we know that there exist square roots, let's say, letters, yes, that contain square roots in terms of the kinematics. We also obtain square roots in this fashion. So I would say that at least for the class of integrals that are expressible in terms of multiple polylogarithms, there should be some generalization of cluster algebras at play. And it would be very interesting to First, study many examples to convince ourselves what the pattern is, and then prove it by first principles, perhaps by the Landau equation analysis.
It's a different mathematical way to think about.
I would think so.
Yet again, no?
We should thank the speaker for a beautiful talk.
Thank you very much for your attention.
And let me call the next speaker, who is Alexander Kusina. Is he joining us remotely or remotely? On strange content of proton and nuclei.
Oh, I should give this to the next speaker.
So I invite next speaker to share. One hour time difference. So if we, yeah, we go to the next one. So the next speaker is Zbigniew Wąs on gauge dependence on spin amplitudes. In fact, the title doesn't say that it's on gauge dependence, but that's what I guess.
So you have a wired connection, right?
Yes.
Okay, so you can join Zoom.
So maybe I will start talking without slides. So my specialty of work was for the last year's Monte Carlo programs. That means spin amplitudes were just things I was using as an input, but then I had to adopt this input to my purposes. And as a consequence of it, I was looking at spin amplitudes from some perspective. So I was expecting to do this fixing while previous talk was going on. So I apologize for some mess. I think I will need your help because I'm not very fluent and usually I have some
Yeah, allow. You can press
Okay.
allow here.
okay,
And yeah, it works.
okay,
And then you can really
no,
video.
stop video, I should press here,
And what you need,
share screen,
share your screen.
so I have to,
Now you have to turn your screen. Screen.
okay,
And
now I have to,
No, you are sharing your screen. What to do is stop it.
Okay.
Yeah. So you can go full screen. Okay. Can we do this?
Okay. Does it work? Very good.
Yeah, it works.
So I would like to say about something about symmetries of spin amplitudes. I had to use it in my work. I got some experience. From phenomenology point of view, when you want to prepare Monte Carlo simulation of other calculations for accelerator experiments, you need to use, of course, fixed order calculations. You need to use resummation. Sometimes you need to use results from dispersion relations, which is a pain because they are anti-analytic. So you need to combine a lot of things from the point of view of detectors, higher orders, and things like that. So there is always a question how to combine these different aspects of work. How in project I participated, I would like to say something, how symmetry was there used. Unfortunately, never was central part of activity, but maybe at the end it's worth to saying a few words about, because it provided some solutions to some challenges. So now, yeah, I have to point here, of course. No? It used to work a moment ago, and now it doesn't. Oh, it worked. Okay. So I will work with examples, my working examples. So first I will talk about QED Brimstone amplitudes for S-channel process. It's different if it's for all processes, so the main process was to be S-channel. Then I will talk about extension in cases when nevertheless some T-channel contribution is added but does not provide structure of singularities. I will say a few words about spin amplitudes for Brimstone in tau decays, because then there is a comparison of results from QED and scalar QED. For continuation, I will jump to some byproduct of calculations, which is spin amplitudes for double Brimstone in QCD, and then a few words about approximation. One of the big words of symmetry in practice, I was fighting to get some orders in terms. So I used independence from the changes of gauge, in fact, of collinear part of the gauge, because the other part of gauge group were not so important. So that's the question of replacing the photon polarization with part which includes collinear momentum, which should make no changes. So there are big difficulties and benefits when one automatic calculations use. One of the benefits is, of course, that you get results. Disadvantages is because you get troubles with tricks like this ones. That's extra layer of activity of trouble. So I will not talk about general factorization, like factorization of tau production and decay. It should be other talk. I will also not talk about separation of big picture. That means when you want to have standard model precision results, you want to divide it into part, which is something like improved Born, something about initial final state effects, maybe some interferences. That's also a huge subject which should be covered elsewhere. I will talk about trivial thing, seemingly trivial thing, but useful. When you have the amplitude, the full amplitude, like M, you want to separate it into product of the two plus correction. You would like to have the product to have some nice structure for iteration, for estimation, but nevertheless have this and the other part it's not. It will change with photon polarization getting longitudinal path. So now everybody can hear me, or okay? So if you work on the other part, we get part of the iconal factor multiplying Born amplitude. And if we combine two such parts together, we get iconal part, which is gauge invariant, and the same iterates if we have many more photons. And because it's QED, because it's Jenifrauschi-Sura scheme, these results are coming out and are immediately useful, and you have all guarantees that it makes sense to go like that. So this is pure pedagogical part, and it corresponds to this, what was done many, many years ago. So the amplitude for double Brimstone can be divided into part which is Born amplitude times iconal factors plus terms corresponding to beta-1 function for first and second photon, and part of amplitude beta-2, which is of double photon emission. Important thing is that all singularities, collinear and soft, are hidden in the iconal factors, and beta-1, beta-2 functions, and of course Born, are all finite, and they do not explode within phase space, and that's important to have this kind of ordering of terms for construction of Monte Carlos. Also, what is very important, that up to the details of definition of MB and beta-1 and beta-2, this scheme can be used all over the phase space. So you do not need to worry about what happens at the edges of phase space. You can make the full coverage, and everywhere you have the matrix element, and it's valid also because of the scheme to all orders. So you have improvement of convergence. So I used some notations and signs from the work which took us several years to construct Monte Carlos for LEP. One of the possibilities to construct of this was that part of the multiphoton, both phase space and matrix element, has extra symmetry, which is conformal symmetry, symmetry of scale, and that helps to organize the predictions. You could make approximate one without phase space Jacobians, lambda 1/2 functions, and then you could add it by after rescaling the later part of generation. So the second extension of it was what happens if one plays with final states of two neutrinos, and two neutrinos can be electrons. Then, of course, appears the problem that you have to take into account emission from W. Your amplitudes are not anymore specifically separating into part for initial state emissions and final state. Final state is absent, except this intermediate state emission of W. So to go with this, you have to make comparisons of two kind of the theoretical scheme. One is iconal QED, and another one is iconal QED with contact interaction. And only after that you can use the old scheme you used in the previous case, and you can add the contribution from W emission dependence on T transfer perturbatively through the beta-1 function. And this goes also with the case of double photon amplitudes. What happens there, and is extra complication, is that you are anymore sitting within a really QED scheme. You even have to take into account with the diagram on the right-hand side where the photon is connected to W and non-physical high fixed field of standard model, which is remnant of the charged Higgs. So you get amplitudes, but it's very difficult to say if you are still sitting within QED or whether you are already going deep into the standard model extension. And the question is whether such scheme will not break the rules, and this has to be gone case by case. So that was the work I did for many years with Dima Bardin and also myself, just to systematize this spin amplitude structure. So QED, scalar QED case. So amplitude for scalar QED is very simple. It's formula number 5. But if you want to get iconal factor out of it, it starts to be complicated because it's not natural to get it, and the correction beyond iconal part is not trivial. It's formula number 7, or you can get a different approach, which are formula number 8 and 9. It depends on how close you want to get for the first part to be iconal factor multiplying Born and what this Born may mean. It's not trivial, and depending on it, you can get different structures. So things, if you go into picture of amplitude squared, you get something which is a little bit simpler. You have combination of Born-like terms, except that fundamenta are combined. So T differs from T prime, but this how the for momentum of photon is used. So spin amplitudes for double Brimstone in QCD. Surprisingly, it's simpler case than scalar QED, and you can get separation first because of QCD operators of SO3 group operators, and then the bulk of the structure game is going out with the structure of Lorentz group. So you can easily separate this amplitude into parts, and as in previous cases, I was not saying it before, the separation is driven by independence on photon, on collinear gluon polarization, and on the structure of singularities. Structure of singularities is related to the boost of Lorentz group. So you can divide the spin amplitude into gauge invariant parts. I will not talk too much about details of this separation, but if you look at it, you will surprisingly find that by combining these terms in different things, you can get terms which corresponds to schemes like BFKL, DGLAB, or CCFM. I will not talk about it, but somehow from the just pure play of symmetry of the amplitude, of finding gauge invariant parts and following the structure of this, that you first group as little as possible to get iconal factor or factor corresponding to collinear and soft emission like formula 12, you get presymptoms of something which correspond, which later on gives factorization schemes. What was surprise to me is when I was studying this amplitude, I found the amplitudes for QCD much closer in nature to those of QED than those of scalar QED. I would think that scalar QED should be closer to QED from geometrical point of view, but it was not. It is maybe because it's not renormalizable theory. So that was the work I did at that time. And then we tried to apply the same scheme for the case emission of pair of fermions. That was for precision simulation, both for LEP and for Bell. You need to have much better precision of final states. So the question of pair emission appear, and the question is how to calculate the systematic error of it. You cannot apply for the algorithm all these diagrams and have something which is universal, which can be applied to any process, even though the calculations for 4 fermion final state exist. You need to combine this with multiple photon emissions, and also you need to have it for all processes. So you want to find something which is universal and precise enough. Unfortunately, from theoretical point of view, the iconal factor for such thing is enough, so that somehow slow down the work. But you may ask how to play and whether you can get something better than that just for the sake of play. And here what you find is that if you look at such process, you can have a lot of regimes, because you may think that par L plus L minus is your main process, and F bar is correction, or the opposite way around. You may also think of it as part of the contribution where you have evolution of parton, which goes from L to F and then back to photon or gluon and L. So you have a lot of options. That means gauge separation into part is not providing something which is very useful. There are simply too many scenarios and you cannot go with them easily. So we tried to play with some options using simplifications. So just to use some gauge invariance separation of the amplitudes and then trying to get something inspired by it. And this gave some tool which could be used for studies of systematic error. It reduced differences with respect to exact calculations of such amplitude by about factor of 4. But at the same time, it is more suitable for iteration, for combining with multiple photon emissions. So it's from the point of view of writing Monte Carlo, which has to give predictions, it's important to have. Maybe not now, but in the future. So in all these games, symmetries help separation of spin amplitudes into part. This was important because we had to deal for the Monte Carlos with fully differential and valid all over the phase space predictions, including some endpoint corners, because that's important for simulations of background, so it cannot for some new physics processes, so experiments wanted to have. This is also very important for multidimensional distributions, which are becoming fashionable these days because of machine learning techniques. So one has to have a control of this. We exposed part of QCD predictions, which look like QED or iconal QED, but not always are this. So sometimes for this QED part, the contributions from charged Higgs had to be taken into account. This is also important because if you need to have predictions of the fixed order combined with higher orders, having separation of this, which needs to be taken at higher orders, is important. This helps to avoid calculation and inclusion of enormous amount of negligible terms. In my talk, I talk a little about loop corrections, which are equally important, partly because from the point of view of Monte Carlo construction, it was less of a pain because they do not bring more complicated phase space, and for Monte Carlo, phase space is important. I was also not talking about similarities of amplitudes for different processes. So when you looked at it carefully, but then you forget in a few minutes, you find out like if there was somewhere a sign of supersymmetry or other algebraic symmetries which combine the functions because of some hidden reasons. So disadvantage of these techniques is that you cannot rely so easily on algebraic methods. If you have Kleist-Stirling spinor techniques or other techniques of that sort, this kind of separation of the part is hidden because it's hidden by fact that you use some auxiliary momentum for defining spin states and for defining spinors in the technique. Anyway, at lab, separation into this kind of the part was indispensable. It's used at LHC2. I don't know how this kind of the techniques will be in the future, but I would think it's worth to keeping this in the toolbox and not in the toolbox. Just be aware that one day you may need to have them. So do not drop the topic out completely. And even if use of it brings a lot of pain, which I remember, it brings also sometimes much rare, but sometimes some fun also, and you may have a feeling that you are touching something of general structure of field theory during the common work when you really want to get predictions for experiments with some precision which is given in per mils or percents, but in hard numbers, absolute numbers. So that's about all what I thought I might talk here about. I hope it will be useful to somebody.
Thank you very much. Do you have any questions? Or perhaps comments? I don't see any. So if not, then we thank the speaker again. And I suggest we try to call the speaker who didn't show up. So I'm not sure if he has a chance to hear my voice, but I'm calling Dr. Alexander Kuzina, who is supposed to talk about strange content of proton and nuclei. He's not responding, so I'm afraid we will thank all the speakers and close the session. Thank you.